Here's an in-depth exploration of some lesser-known facts about electricity, expanded to give a comprehensive look at each fascinating point. Let's dive into the science, history, and real-world applications of each one. Factor 1. Electricity travels long distances with surprising efficiency. The world's reliance on electricity is built upon its ability to travel across great distances with minimal loss. This is possible because of alternating current, AC, a type of current that can be easily transformed to high voltages and then stepped down at the point of use. The higher the voltage, the lower the current, which reduces resistance in the wires and allows electricity to travel hundreds or even thousands of miles efficiently. The debate over using AC or DC power systems dates back to the late 19th century, when Nikola Tesla and George Westinghouse argued for AC over Thomas Edison's DC approach. While DC works well over short distances, it's challenging to transmit over long distances without substantial loss. AC, however, enabled the creation of power grids that could supply electricity to entire cities, reshaping industry and modern life. Today, most countries use AC for their electrical grids, although there's renewed interest in DC systems for specialized applications, like in data centers or high-voltage DC transmission lines for very long-distance intercontinental connections. This efficiency of transmission makes AC a backbone for modern life, though DC is seeing a resurgence in specific niches, especially as we explore renewable energy storage options. At 2, almost as fast as light. Electricity might seem instantaneous, but what's actually happening is complex. In conductive materials, electrons themselves don't travel at the speed of light. Rather, it's the electric field that moves quickly. When you flip a switch, an electric field propagates through the wire, influencing the electrons along its path almost immediately. This field moves close to the speed of light in some materials, making electric-powered responses nearly instantaneous. This rapid speed is essential for numerous applications, from your home's lighting to global communications networks. Imagine if there were even a small delay. Our digital world, with all its rapid data exchanges, simply couldn't function. Innovations in materials science are now exploring superconductors and photonic systems that could push the boundaries of electrical and even light-speed communication further, with implications for computing, medicine, and beyond. Chapter 3. The Earth itself is electrically alive. Electricity isn't just in our walls, it's in the atmosphere, and the Earth's crust itself. Known as the key global atmospheric electrical circuit, this system includes thunderstorms, which act like giant electrical generators, recharging the Earth's electric field. These storms release electrons into the atmosphere, which in turn contribute to a constant, albeit weak, electric field that surrounds our planet. This field isn't just interesting, it's fundamental to certain natural processes. It's also a research interest for scientists studying lightning, weather patterns, and even climate change. The electric field may have also played a role in the origins of life on Earth, providing the energy needed to form basic organic molecules in early Earth's atmosphere. The continuous recharging of the Earth's electric field by thunderstorms reminds us that our planet is electrically dynamic, a characteristic that extends beyond lightning storms to phenomena like earthquake lights and boat sprites, mysterious flashes above thunderclouds, which scientists are still working to fully understand. And 4. Your body is an electrical network. Humans aren't just chemical beings, we're also electrical systems. The body relies on bioelectricity for every movement, thought, and heartbeat. Neurons, the cells responsible for sending messages in the brain, communicate through electrical impulses that pass signals between each other. This electricity is generated by ions moving in and out of cells, creating small charges that allow signals to travel. The heart too operates on bioelectricity, relying on an electric impulse to keep a steady beat. When this rhythm is disrupted, devices like pacemakers send electrical signals to correct it. In fact, the field of bioelectricity is now central to several medical technologies, including brain-computer interfaces and neural prosthetics, which are advancing the ways we can interact with and assist the human body. This network also plays a part in our senses and in healing. For instance, researchers are studying electric fields in wound healing to understand how electrical impulses can direct cell growth and regeneration. Understanding our bioelectric nature might one day lead to new treatments for a range of neurological disorders, offering a powerful glimpse into the electrically powered machine that is the human body. Lightning, more than just a flash. When a lightning bolt streaks across the sky, it's not just a beautiful spectacle, it's an immense release of energy. A single bolt can reach temperatures of up to 30,000 Kelvin, 53,540 degrees, which is around 5 times hotter than the surface of the sun. This heat causes the surrounding air to expand rapidly, creating the thunderous sound we hear after the flash. A lightning strike carries enough energy to power a 100-watt light bulb for about 3 months. However, capturing this energy for practical use is nearly impossible due to its unpredictable nature and the incredible force of each strike. Some scientists are, however, studying ways to safely harness lightning or mimic its power, which could open the door to new renewable energy sources. Beyond its raw power, lightning plays a key role in Earth's ecosystem by fixing heat or nitrogen in the soil, which helps plants grow. Every time a bolt strikes, it breaks the molecular bonds of nitrogen in the atmosphere, allowing it to combine with other elements and create nitrogen compounds essential for plant life. So, while it may be destructive, lightning is also a force of creation. 6. Electric eels, nature's high-voltage power plants. In the world of electric organisms, electric eels are remarkable. These fascinating creatures generate shocks up to 860 volts to stun their prey or deter predators, making them one of nature's most potent natural powerhouses. They have specialized organs filled with cells called electrocytes, which act like tiny batteries that discharge simultaneously to produce a powerful electric current. Electric eels use electricity in 3 ways: to navigate and sense their environment, to communicate with other eels, and as a weapon. This ability gives them an evolutionary advantage, allowing them to thrive in murky waters where visibility is low. Scientists are studying these eels to better understand bioelectricity and how it might be replicated. If we could mimic the way eels generate and store electricity, it could lead to breakthroughs in pet biological batteries, or new ways to create sustainable power sources for medical devices, wearable electronics, and even small robotics. 7. Beware. Static electricity can be a hidden danger. Static electricity can be more than just an annoying shock. It can be dangerous and even deadly in certain environments. In industries dealing with flammable materials, static sparks can ignite gases, vapors, or even dust particles, causing explosions and fires. For example, oil refineries, chemical plants, and grain silos all use anti-static equipment to prevent such accidents. This happens because static electricity builds up when 2 surfaces rub against each other, causing an imbalance of charges. When this charge finds a path to discharge, it can create a spark. In a normal setting, it's harmless, but in environments with volatile substances, that spark can trigger a chain reaction. To prevent this, workers wear grounding devices and anti-static clothing, and workspaces are designed to minimize friction and provide safe grounding paths. Understanding and managing static electricity is essential for safety in industries where a single spark could be catastrophic. Act 8. Sharks and other fish. Sense electricity. Imagine navigating in pitch-black waters with no light, yet still being able to detect your surroundings. Sharks and certain other fish can do just that by sensing electrical fields generated by other animals' muscle movements. Electroreception, as it's called, allows these animals to detect even the slightest electric field changes in the water. Sharks have specialized organs called ampullae of Lorenzini, located around their snouts, which detect electric fields and help them track prey, even if it's hidden in sand or murky water. This adaptation gives them a hunting edge, allowing them to detect and capture food that would otherwise be invisible. This skill has inspired research into bio-inspired sensors and robotics, which might one day enable underwater robots or search and rescue drones to navigate and detect objects in low visibility conditions. Scientists continue to study these electroreceptive abilities in the hope of applying them to technology and even medical devices, like tools that could one day navigate within the human body with unprecedented precision. 9. Electric wind can cool you down. Silently, when electricity flows, it can sometimes create a phenomenon known as electric wind or ionic wind. This effect happens when charged particles in the air are attracted to an object with an opposite charge, creating a gentle, invisible breeze as they move. This electric wind can be used in silent cooling systems. Unlike fans or air conditioners that rely on moving parts, electric wind cooling uses ions to create a breeze without noise or vibration. This has potential applications in cooling electronics, smartphones, and even quiet, efficient climate control systems in homes. Researchers are working to make this cooling method more efficient, with the goal of using electric wind for large-scale cooling applications. Electric wind could soon be the key to quieter, energy-efficient cooling, changing the way we approach temperature control. 10. Electricity, more than just metal. When we think of electricity, we often picture metal wires, but electricity can travel through various other materials. Water, for example, is a good conductor because it contains ions, charged particles that allow current to flow. This is why swimming in salt water during a storm is extremely dangerous. Water can conduct lightning, putting swimmers at serious risk. Human bodies, which contain water and ions, also conduct electricity. This property is why defibrillators can send a jolt through the body to restart a heart. However, it's also why electrical accidents can be fatal, as electricity can disrupt the body's natural bioelectricity. Understanding how different materials conduct electricity is essential for developing new technologies, including wearable electronics, bioelectric devices, and saltwater energy sources. It expands our understanding of electricity as a force that goes beyond metal wires, potentially unlocking new frontiers in science and medicine. Ready to plug into the power of knowledge? Electricity is far more than what flows through our wires. It's an incredible force shaping life, technology, and even the atmosphere. As you marvel at the sheer power of lightning, the elegance of an electric eel, or the innovation of electric wind cooling, consider the endless possibilities electricity holds for the future. Are you ready to uncover more about the electrifying world around us? Dive deeper, learn more, and be part of a movement toward harnessing electricity in sustainable, life-changing ways. Let's stay curious and let the knowledge spark new ideas that might one day power the future.